Good evening, lovely humans. I hope you are all doing okay. I missed you all a lot. So, yeah. Today we're going to be going over section 931 and the other two problems from the classwork, 970 and 973. So, I'm going to kind of talk you through 970A and B, and then I'll show you a calculator I used for part C. And then we'll talk through part D. And then for 73, I'll go to the E tool to work through that. So for 9-70, so a data set, in order to make, this is important, so in order to make the standard deviation of a sample more closely estimate the population's standard deviation, so like if you just sample like 100 people, but you want it to represent the whole population, then statisticians actually modify the way that they calculate standard deviation for the sample to kind of account for the smaller sample size. Okay, so if the data set contains the entire population, what we learned was that when you're calculating standard deviation, you divide by n the number of values in the data set. If the data set is a sample from the population, though, you're going to divide by n minus 1. So which standard deviation is going to have the larger value? Well, let's think about a number, right? So n and n minus 1 are a little confusing, but let's think about if n was 10, right? So if you divide by 10 versus dividing by 10 minus 1 or dividing by 9, which one of those is going to be bigger? So division is backwards, right? So dividing by the smaller number actually gets you the bigger answer. So that means that if our data is a sample, then we divide by n minus 1 to make the standard deviation a little bit larger to account for the fact that there may be more deviation in the whole population. Okay, so one of the reasons the sample standard deviation needs to be increased has to do with outliers. This is part B. Why might the presence of outliers in the population make the standard deviation of a sample too small compared to the standard deviation of the population? All right, so if you just take a sample, you might not get all of the outliers that you would in a situation. So that means that the standard deviation of the whole population, if you account for the outliers have a really large distance from the mean. That's like the definition, right? So it would mean that there would be a larger standard deviation, right? When you take the square root of all the distances squared of distance from the mean, that whole value is going to become larger once you introduce outliers. So that's why we have to divide by n minus 1 to kind of help alleviate some of that artificial smallness of the standard deviation. All right, so we're going to look at problem 65, but we don't care about 65. We really just care about these numbers, 60, 60, 50, 40, and 50. It says to explore the functions on your calculator to find the mean and sample standard deviation for the 5 birds. Well, if you don't have your graphing calculator, fear not, we shall look one up. Standard deviation calculator. Math is fun, love it. Let's go ahead and type in those values. We have 60, 60, 50, 40, 50, something like that. Yeah. And what we want to say for part C is that this is a sample, right? So it tells us there are 5 numbers. The sum is 260, which means that our mean is 52. Thank you, technology. And then it tells us down here that our standard deviation is about 8.37. Remember, this is for the sample. So that is what we want to use for part C. We want to use the fancy symbols, right? So if you go back, zoom this out. So you want to use X bar for the sample mean and then S for the sample standard deviation. And that's something statisticians do to let the reader know that you're talking about the sample mean and the sample standard deviation. And then for the population mean and the population standard deviation, we use this little Greek letter called mu and this little one called sigma. So let's go ahead and calculate it. You can change it up here for the population and see that your standard deviation will be about 7.48, which we represent with little sigma. And I do believe that that concludes 9-70. So let's go ahead and take a look at 973. All right, so the 40 women in the sample recorded their race times in various charity 5K races in the table below. Explore using the 973 e-tool. Really, this was for a 5K? Those are some fast women. Okay. So we're going to find the mean and standard deviation of the race times to 4 decimal places. And we're going to have to decide if we want to use the sample standard deviation or the population standard deviation. So we have to decide, is this the entire population? Well, no, it's 40 women from a sample, right? So we're going to have to use the sample standard deviation represented by the letter S. So let's take a look at the e-tool. The e-tool came up super weird on my computer and I had to mess with it a little bit. So here's my messed with version that's a little bit easier to read. And if you click on single variable statistics over here, if you scroll all the way down, single variable stats, this lovely thing pops up in the top right where it tells you your standard deviation of the sample and of the population, right? So we want to write down 0.9729 for our sample standard deviation and 23.2175 for our mean, using S and X bar, the correct notation. For part B, we want to look at creating a relative frequency histogram. So if you're having issues with this, go ahead and take a look at the classwork from classwork number 1, the one right before this, where it goes over how to make a relative frequency histogram. It's not too hard. You basically just have to take each bar's height. So for example, right here, there's only one person that came between 20 and 21 minutes. And so that would be 1 divided by 40, and that would be the new height of your bin. So 0.025 for that first one. Again, if you're still confused, please email me, come to our video conferences, do what you need to do. I'm here to help. Okay, and then part C asks how many people received a better mile time than 22, or a better race time than 22. So remember that we're looking for the numbers lower than 22. So you're going to add up the percentages, which are 5% and 2.5% once you calculate these guys, and you'll get 7.5%. And then part D is the same kind of process. It also has you point out that on a relative frequency histogram, so that's not what we're looking at, unfortunately, but if we were looking at a relative frequency histogram, easy for me to say, then the area of each bar actually represents a percentage, which makes it really ideal to look at. So if you are just looking at the area of a bar on your relative frequency histogram, and the area of it is 0.025, and like in the case for this 20 to 21 bar, then the percentage would just be 2.5%. So area is the same as the percentage. All right, and that is all we have for today. So I hope you have a fabulous rest of your day, and I'll see you next time.